Greetings YouTubers, and welcome to another installment of the Backpacker Fact Checker. In this series, each episode investigates one of those trail tales that tend to be repeated over and over again without ever being proven. Number one was on shoe weight and the claim that 1 pound on your feet equals 5 pounds on your back. And number two looked at the idea that you lose 40 to 45% of your heat through your head. To view the series, see the playlist link in the video description box below. This video examines the ramifications of inflating a sleeping pad with your breath. And there are two main issues to consider. First is the idea that the humidity in your breath lowers the effective R value of your pad, making you sleep colder. And R value is the insulation rating of your pad. The R stands for resistance to conductive heat flow, and it comes from the construction industry. The R value for the fiberglass insulation in your walls is the very same rating system for backpacking sleep mats. And the second issue involves the concern that introducing moisture into a pad results in mold growth. And I'll do my best to look into both of these concerns and show you exactly what I found. Now, the fact checker format sets up the familiar true or false rating system. As we saw in parts 1 and 2, reality is often more nuanced than that. So as with every video I make, the conclusions are just my take. The information is there for you to decide. So regarding that first issue, does humid air have a lower R value than dry air? And I've seen this asserted repeatedly on certain backpacking channels, usually in the context of why you need to buy one of these. But no evidence is ever provided. Well, any scientific claim that's made without references always piques my interest. It also appears on blogs. In the span of a single article, both of these statements are made. Notice the change in terminology. First, it's the word humidity, and then later when the claim is restated, the word moisture is used instead. That's an important distinction we'll come back to, but for now, let's stick with the issue of humidity. I should get t-shirts made. As it turns out, there seems to be remarkably little research on the subject. I eventually found this paper from 1996 on the properties of humid air, published in the Journal of Physical and Chemical Reference Data. And in it, the authors state there's only been a single measurement reported for the thermal conductivity of humid air. And it was by Groos and Schmick in the year 1928. So figure 3 shows their data with a solid line for the theoretical curve that extends the results past what was actually tested. And this would be difficult to apply to our circumstances for a number of reasons. The horizontal scale represents the mole fraction of water in the gas mix. On this end, you'll have perfectly dry air with no humidity whatsoever, and that does not exist in nature. On the other end, you have nothing but water vapor with no air in it at all. So this graph consists largely of circumstances that would be impossible to find in the actual atmosphere, and all of this was done at a temperature that would roast you like a tomato. Not exactly trail conditions. Still, the takeaway is that water vapor has only 3/4 the thermal conductivity of dry air. Generally speaking, then, the more water vapor you add, the less of a conductor that mix will be. And that would tend to make humid air a better insulator, not a worse one. Now, you may have noticed this slight bump in the beginning where the conductivity actually goes up a bit before starting to fall. Well, first, that's coming from absolute dryness, which you will never get outdoors. Starting from a position of some humidity, it's still mostly a downhill game. But also, notice the suppressed zero on the horizontal scale. The graph essentially shows only a tiny slice off the top of the whole picture. And this serves to significantly exaggerate the appearance of this bump. Looking for a second take, the authors note that since air consists mainly of nitrogen, data for the thermal conductivity of a nitrogen-water vapor mix can be regarded as a further source of information. And they provide that data in the form of Table 12, tested at 65 C, which is still unreasonably hot, but getting closer to reality. And it exhibits a similar pattern to the previous test results, with a slight increase in the beginning before a more substantial drop later on. Well, I charted these numbers without the suppressed zero to give better perspective on the scale. And as you can see, that alleged hill in the beginning all but disappears, being almost too slight to notice. So coming from a position of some initial humidity, yes, it's technically all downhill the more water vapor you get. But it's fair to point out how relatively flat this whole region really looks. There's a difference, but it's not much. So apart from that, the only other thing I could find was this article on the thermal conductivity of moist air. This author also notes that the thermal conductivity of air has been the subject of few contributions. He does get regularly asked about the influence of humidity, and his standard answer has always been nothing to worry about. The colleague of his found software that uses kinetic theory to model the mixture of atmospheric air and water vapor, and it produced the graphs in Figure 1. Here again, as moisture content increases, the thermal conductivity decreases. Thermal conductivity is here, and the colored lines represent different percentages of humidity with the temperature along the bottom. And this shows that as humidity increases, the lines bend down. The humid air becomes less of a conductor. And the swanky shapes come from the fact that as temperature increases, this also serves to reduce the conductivity. So theory says, backed by some experimental data, that humid air, like that from your breath, should actually make your sleeping pad a better insulator, not a worse one. So based on that, I'd be inclined to rate the initial claim as false. However, we can keep making it more complicated. What I've been talking about is your typical uninsulated inflatable, like this Thermarest NeoAir X-Lite. The term insulation gets used imprecisely in product marketing sometimes. Used here, insulation means some kind of filling, something you stuff the pad with to improve its R value. And yes, the X-Lite has an R value of 4.5, and it gets that from two main things. They put a reflective layer inside, and that helps bounce back some of the radiative heat loss. We're only talking here about conductive heat loss from actually touching the cold ground. Put a space blanket on the snow and lay on it. You'll find out quickly how useless they are in that respect. So what protects you from the conduction is the gas you blow in, and that air gap is what slows down this kind of heat transfer. The heat doesn't conduct through gases in the same way it does through solids. The individual molecules aren't bound together, so there's no actual touching in a conventional sense. Heat must pass across a gap bit by bit through a series of collisions between those loose gas molecules. And this is part of what makes air a good insulator. It's a relatively slower way to transfer heat. And they also talk about mean free path. This is the average distance you would have to travel in a random direction before you'd bump into one of those gas molecules. If you decrease the mean free path, a hot molecule on one side won't get as far before colliding with someone on its way to the cold side. So more collisions will be required to keep passing that heat onward, taking more time. So humidity helps lower the mean free path of the air mixture, and that's why it contributes to slowing the rate of heat transfer, reducing its conductivity. Right, so where am I going with all this? That all applies so long as the humidity remains humidity, which is to say the water remains vapor. The water vapor is a gas. You can breathe on a mirror and see what happens. Hot air can hold more water in gaseous form than cold air. When your warm, humid breath hits the cooler surface of a mirror, it suddenly loses its ability to hold all the water suspended within it. So excess humidity, if you will, rapidly condenses out of the air and onto that chilly surface. Now it's not vapor anymore, it's liquid water, albeit in some very, very tiny drops that appear as the fog you see. And you can wipe it with your finger to feel the wetness. Well, if you're blowing up your pad outside where it's cold, this can happen on the inside of it. What might the implications be for the R value then? I did not find any actual testing, so this is just me talking, and I always want to point that out so you can take it for what it's worth. Personally, I don't think it would have much, if any, effect on an uninsulated inflatable. So suppose this was a cutaway view of your pad, with this being the top layer and this being the bottom. And I know they do things like put baffles inside, but it's all still just a series of air-filled gaps. To simulate condensation within the mat, let's put some water along the inside of both the top and the bottom. And if you were to view this condensation through a microscope, it's a series of unconnected droplets, however tiny. And even though this is liquid water, which has a much higher conductivity than air, the heat must still travel across these gaps, still conducting as a gas. What about if the pad has some kind of filling? Xbed, for example, makes the Ultra 7R. It's an inflatable pad, but it's also filled with down insulation like a sleeping bag. I could not find any studies, but something like this could at least potentially change the game. Through the construction industry, it's very well known that moisture can compromise the effectiveness of insulation. Wet insulation retains less than 40% of its effective R value, according to DuPont. And that's why builders use moisture barriers like Tyvek to keep the insides of your walls dry. The wet head makes a good example. Water mats the hair down. Well, your hair, not mine. I wash my hair with hand soap and shake dry like a dog. Anyway, a wet hairdo loses its loft and those insulating air pockets get replaced with highly conductive water. And by one account, absorption of only 20% moisture can cause up to a 55% loss of insulation value. Remember at the beginning I said we'd come back to the distinction between humidity and moisture? This is that time. A 20% relative humidity is a completely different situation than 20% moisture absorption. That humidity is still water vapor, and it conducts slowly as a gas across an air gap, as discussed previously. Moisture, however, is a liquid. If enough of it gets absorbed into a physical media like the insulation in a pad, you can effectively get a direct pathway for conduction. It's almost like connecting your body to the ground with wires made out of water that conduct heat instead of electricity. Well, this obviously could affect the R value and make the pad feel colder, theoretically. But practically speaking, how much of a concern is this really? Well, the short answer is, I don't know. It seems like it's at least technically possible, so to attempt to guess, we should consider approximately how much moisture we might be talking about. I found this estimate for the water loss through respirations while panting heavily, hiking uphill, and that works out to under 1/10 of a milliliter per deep breath. And assuming that you would use similarly sized breaths to inflate a pad, let's do some garage science. I weighed my regular sized NeoAir X-Lite while dry at 338 grams. It takes me 13 deep breaths to fill it up. In an attempt to deliberately accumulate moisture inside, I deflated and reinflated it 3 times in rapid succession. And all of this was done in the cold to try and convert as much of that breath humidity into liquid condensation as possible. And then I weighed it again, 341 grams this time. So that's 3 grams of water clinging to the inside, or a gram per inflation cycle. That also works out to about 0.077 grams of water per breath, which is a little lower than James's estimate, but logically it really ought to be. Not all of that condenses into surface moisture. Some will remain as water vapor and be expelled when you deflate the pad. So if we pretend his estimate is perfectly accurate, that means I'm getting about an 80% condensation rate, with the remaining 20% staying gaseous and being removed in the exhaust. So for a more visual demonstration, I did the same thing with a 1-gallon Ziploc bag. And this is what it looks like after 5 successive inflations. The bag gained 0.55 grams of water weight, so that's 0.11 grams retained per inflation. And at about a breath and a half to inflate each time, it works out to 0.073 grams per breath, which is surprisingly close to the 0.077 grams per breath measured for inflating the sleeping pad. And by shaking it, you can get the microscopic stuff to aggregate into some very tiny droplets. Now remember that I performed multiple inflation cycles back to back to deliberately accumulate moisture so that it would be enough to reliably measure and then divide. And this is 5 times what you get from a single inflation. So I guess the question is, would 1/5 of this fine mist be enough to compromise a bag full of insulation? Again, I don't think that moisture would noticeably hurt the R value of an uninsulated pad. Yes, there's some water in there, but it's nowhere near enough to directly connect you to the ground in a thermodynamic sense. Heat transfer from the back to the front of the bag still has to conduct across that relatively huge air gap in the middle. And if you want to argue that heat can travel around the outer surface via that moisture, remember those mist droplets don't actually touch each other. But with insulation inside, you've got something that can soak up that water and physically form a bridge between opposing surfaces. So how much water from how many breaths would it take to lower the R value of an insulated pad by 1? There are so many variables and no testing that I can find. It would depend on the outside temperature, which might control the condensation rate. It would depend on the amount and type of insulation in your pad and its ability or resistance to absorbing water. hydrophobic down might not be nearly as bad as a self-inflating pad filled with absorbent foam. And perhaps most importantly, it could depend upon whether the moisture from each day's inflation builds up over a longer trip. 3 inflations, one right after the other, is an artificial situation. And in field use, a more realistic scenario is 1 inflation per 24-hour period. Well, that gives any condensation inside quite a bit of time to evaporate back into vapor. And contrary to what you might assume, our breath does not come out at 100% relative humidity. And granted, it's a pretty wide range given, but it can actually be less than 50%. And that leaves a fair amount of room for moisture to evaporate, even in a chamber filled with humid breath. So watch the mirror again. You can see the moisture disappearing back into the air, and that happens even though the mirror isn't warming up. But what do you do with a pad after you've blown it up? You proceed to lay down and warm it up with your body heat, and that will help re-vaporize internal condensation. It would be like me warming this mirror with my hands to help it clear up faster. So I tried a simple test. Starting with a dry pad at 338 grams, I blew it up in the cold to provoke condensation. Then I laid on it for 2.5 hours while I watched a movie, after which I immediately deflated and waited again. Right back at 338 grams. To within the nearest gram, it gave back all the moisture it had taken on. And true, it could take longer when on the cold ground, but over the course of a whole night, you'll lay on it at least 3 times longer than I did. And as always, there's room to argue about the details, but the point is this. Used normally, a pad does not simply add each day's inflation moisture to the last. In non-extreme circumstances, within reason, pretty much all of that appears to be expelled each time you empty the air out. And one suggestion would be to deflate each morning while the pad's still relatively warm from your body. Don't let it chill off first by leaving the tent. There's at least the potential for a recondensation. And really, if you think about it, this shouldn't be the subject of much controversy. If there was even a small amount of continual accumulation, through hikers at the end of the AT would be able to tip the pad up and literally pour out the water. And this obviously isn't the case. So you must be able to routinely come pretty darn close to breaking even with each inflation-deflation cycle. So that being the case, given my numbers, I'm never looking at more than 1 gram of water inside on any given day. Well, this is what 1 gram of water looks like. Now, if we smear it around, it'll help give you an idea of how much that moisture can cover. Now, this area is barely the head and shoulders portion of a regular-sized air mattress. Now imagine trying to spread it out over the entire length of a 6-foot pad while expanding it into a volume 3 inches thick. It will all but disappear, which is probably something that helps it evaporate better. Seems unlikely that that amount would make a change that you could feel. Now, I did try to test the difference between a dry inflated pad and one full of humid breath, but I don't think my equipment made for a particularly accurate experiment. My shop floor is a very large slab of concrete, so it makes for a huge heat sink. And I marked off 2 spots far enough away from each other to avoid interference. And then I laid the inflated pad down with a weighted heating pad directly over the marked spot. And after an hour, I checked the temperature on the concrete below to see how much heat had made it through. And I'm using a Thermal Pro non-contact infrared thermometer, which I can watch fluctuating back and forth, plus or minus 0.2 F, even though I'm holding it still. And I prefer a tighter margin of error than that, but it's all I've got. Anyway, I found no statistically significant difference between the heat transmitted by a dry pad versus a humid one. And given what we've seen about how likely small the effect is, this is probably what we should have expected. Okay, that was all for a pad without any stuffing inside. And for my part, I currently only use the air-filled Thermarest pads. I don't have any testing to show how moisture accumulation might be affected by insulation. Going way back though, I've done 11 days unsupported in the cold but not freezing Canadian backcountry using a self-inflator. And despite the absorbent foam-filled interior and that many days of consecutive inflation, I never noticed any loss in warmth over the course of the adventure. Now, it all could get more serious, though, if you're pushing the limits of your sleep system and it's dangerously below freezing outside. Maybe that's why XPIT includes a pump sack with their down mat, just to be on the safe side. As far as the issue of mold growth goes, I've personally never experienced any. I poked around on the internet looking for complaints of mold. I found a few allegations like this one, a picture of the outside of a pad. And here on YouTube, there are some folks that actually cut their pads open looking for mold. Adventure Bird did a video where she destroyed her pad for science. You gotta respect that. And to her credit, she admits being convinced ahead of time that there would be mold. She had held the pad up to the light and could actually see spotting inside. But upon ripping it apart, she found no mold, in her words, at all. What she discovered was that the heat reflective coating had begun to flake off in places. And this is what caused the spotting visible when shining a light through the pad. Backcountry Exposure did a similar video. He took a pad that was 8 years old and had experienced hundreds of inflations. And when he sliced it open, there was no mold to be found, not even near the mouthpiece. He concluded that the mold myth was busted, and he also identified flaking mylar in certain spots. And I like his channel, by the way. He does a lot of different kinds of hiking, and he's honest about his mistakes, which I respect. And then World Survival cut open his self-inflating pad to see what had happened to the insides after 10 years of use and admitted poor storage conditions in his garage. Now, this is the kind of pad with foam inside. If there ever was a pad to have mold, he said, this would be it. And he found not a single bit. Nothing, not even near the valve. So admittedly, this is one of those situations in logic where they say you can't prove a negative. Just because some people, or many, or even all people so far haven't found mold doesn't mean it can't happen. All I can do is tell you that I found no credible reports of actual mold on the inside of a pad. Science is ever changing and nothing is considered immutably certain. So for this fact check, I have to go by what I've got. And so on that basis, I'm giving the claim that your breath will cause a pad to grow mold another false. I did not find any even semi-scientific evidence that this is true. And this seems like a good time to try out my new message. Okay, time for the summary. It gets repeated without proof that blowing up a pad with your breath will lower the R value because humidity. It is then recommended you spend money on and carry the extra weight of some kind of pump. However, rigid sphere gas theory suggests that water vapor actually lowers the thermal conductivity of air, which could make a humid pad a better insulator, not a worse one. And the possibility of condensation complicates the issue by potentially turning some of that humidity into tiny water droplets on the inside surface of your pad. And under reasonable conditions, this does not appear to accumulate over successive inflations. And the amount of condensation from any one inflation is small. So for non-insulated pads, a tiny amount of moisture around the edges won't change the fact that it still insulates via an air gap as a gas conductor, not a liquid one. The difference between dry-filled and humid pads in the operable range of any realistic field conditions is quite small, though, and not likely to be noticeable on trail. For pads filled with some type of insulation, there are some unknowns, like how much the insulation will absorb, how easily it dries out between uses, and what the effect of a tiny amount of moisture would be. If you use an insulated pad in extreme conditions, and or like to be on the safe side, you could consider carrying a pump if for no other reason than the peace of mind. And for your standard air-filled pad, however, there appears to be no foundation for the concern that blowing it up manually will cause you to sleep colder. And as far as the second issue of mold growth from humidity goes, I found no credible evidence of this actually happening. Pictures of the outside of a pad don't count. Anecdotes without evidence don't count. All of the instances I found where people actually cut open their pads to check found not one bit of mold, even from pads used for many years. Now, I personally have never carried a pump and will continue not to. That being said, there's nothing wrong with doing so. These pumps are getting amazingly small, and if you have any kind of problem blowing up a pad on your own, a pump can be a benefit. The good ones can double as a lantern, and some even let you utilize the internal battery as a power bank to charge your other devices. Or replace one of your stuff sacks with a pump sack for a small amount of extra weight and the assistance that it provides. And you've got options, and I never make a video with the intent to tell you what you should or should not carry. It just bugs me like an itch I have to scratch when I keep seeing what amounts to a scientific claim made without a shred of supporting evidence. I gotta look into it. I gotta. Sometimes that research provides more definitive answers, other times it leaves gray areas. My only real goal with the Fact Checker series is to hopefully leave you more informed about the topic than before you came in. Even if nothing you see changes your mind, at least now you got something to base your conclusions on beyond just what intuition says. And if that happens, then mission accomplished. As always, I very much appreciate your time, and thanks for watching.